I'm going to finish up this chapter 10 on moment of inertia by picking up a few last miscellaneous topics. We'll talk about radius of gyration, how to handle composite areas or things that are made up of different shapes, and finally the last topic will be mass moment of inertia, which you will use in dynamics. The area moment of inertia, which we've done so far, is what you'll use in mechanics of materials. So a quick review, we've learned that Ix equals integral y squared dA, and Iy is integral x squared dA, and these usually are taken about the centroid. And when you want to get the moment of inertia about not the centroid, you take the moment of inertia about the centroid plus a d squared, and these things are in tables. You don't actually have to do those integrals. So here again you see what I just said, Ix and Iy. I forgot to mention that the polar moment of inertia is r squared dA, and because r squared is x squared plus y squared, the polar moment of inertia is just Ix plus Iy. And again, here is the parallel axis theorem to get the moment of inertia about a new axis. You take the moment of inertia about the centroid and you add AD squared. Okay, the next topic is called radius of gyration, and it's all about getting averages. So remember the centroid, x bar was the integral of x dw all over the integral of dw. Remember, it's just like a GPA. Y bar is integral y dw over dw, and z bar is integral z dw over dw. Well, what if you wanted to get the average x squared? Extending that concept, it'll be the integral of x squared dw all over the integral dw, and that would be the average x squared, which is not average x squared. I mean, average x squared does not equal average x all squared. That's not the same thing. The radius of gyration is just related to this average x squared. It's just begging to have a square root taken. And so if you take the square root of this, you get what is called the radius of gyration. It's just the square root of the average x squared. And if you plug that all in, this is what you get. The integral x squared dw in the numerator is integral ix, and the integral dw is a, well actually all those dw should be dA, sorry. And then you get Iy over a square root and polar moment of inertia over a square root. So all you do is you get the moment of inertia divided by the area, and then take the square root, and that will be the radius of gyration. The next topic is composite areas, or how do you eat an elephant? So the answer is one piece at a time. So if you had a tail, I don't actually know how to draw an elephant, legs, ears, and a nose. What you would do is, to get the polar moment of inertia of that, you would break it up into pieces that hopefully you could find all in the back of the book. You do it one piece at a time. If you want to find the I about the centroid, find the overall centroid of all the pieces, and you can sometimes do this just by looking. So for example, if you had an I-beam and it was completely symmetric, obviously that's the center of gravity. And then what you do is, once you do have a piece, so let's say you had a T, you found the centroid, step number 2 is now you make the centroid your new origin, and then for each piece you're going to calculate I equals I0 plus AD squared. So let's say this is the overall centroid. You'll take this piece, get the moment of inertia about its axis. This distance is d, And so the moment of inertia about the overall centroid would be I0 plus AD squared. And then you would do the same thing for this other piece down here and add it all up. It is easier to do this in a table, and Excel is fantastic at making tables. So here's example 10.4 from the book. You can go look at that. What I did was I took example 10.4 and put it in Excel. I got the area, I got the eye of the rectangle and the eye of the circle by looking in the back cover of the book. Note that I made the moment of inertia negative for the circle because we're cutting it out of the rectangle. I got the area of the rectangle and the area of the circle, again, a negative area. And then I found the distance of each from the centroid. Oops, the distance about the centroid is 0 because the centroid is right in the middle. But it's asking us to find the moment of inertia about the bottom. So the distance from the centroids to the bottom were both 75 millimeters. So you have 75 and 75. And then I had Excel take the area multiplied by d squared. And even though the d squared is positive, the area was negative. And so you still get this negative. I added up I0. This column here is I0 plus AD squared. And so I got that and that. And when you add them all up, this is the total I about the bottom. Similarly, I redid example 10.4 in Excel. That's piece 1, piece 2, and piece 3. And I've posted these slides as PDFs so you can look at them. And they wanted to know moment of inertia about the x-axis and moment of inertia about the y-axis. And for each piece, you just get I0 about the x, so about each individual centroid, the area, the distance in y from the overall centroid, and then AD squared, and add it all up, and then the final sum. And I repeated it for y, IY, which uses x distances. And finally, I'd like to talk about the mass moment of inertia, and we are going to use our friend Letterman again. So remember, Letterman can change any letter in an equation, and so to get the center of mass from the center of weight, remember, we just used Letterman, and he changed all the W's to M's. And that's how we could do center of mass, even though we knew the center of weight before. Just change W to M. Well, similarly, what we're going to do is use something called a moment of inertia. And we had R squared dA, but now we're going to have R squared dM. And very, very confusingly, we're going to call it I, not J. And so I know this is confusing, but this is the equation for mass moment of inertia, even though it looks like the polar moment area. And if the density is constant, you can factor out the density times dV, and you get this final equation here. What I want to emphasize is this. For mechanics of materials, ES 2410, you are going to use this one, x squared dA and y squared dA. For dynamics, ES, I think it's 2120, you are going to use this one, I equals integral R squared dm. When you hear moment of inertia in mechanics of materials, it is area moment of inertia. And when you hear moment of inertia and dynamics, it's mass moment of inertia. And what's very confusing is that you will probably take both these classes in the same semester, and one professor will be saying moment of inertia and mean this. That would be your mechanics of materials instructor. And another professor will be saying moments of inertia and mean this, and that would be your dynamics instructor, maybe me. Just remember, mechanics of material, area moment of inertia, and dynamics, mass moment of inertia.